CITA Blackboard seminars. It's my favorite time of the week, even when I'm not giving them. Well, especially when I'm not giving them. So what I want to tell you about today is the sort of current state of a project that I've been working on for a while now with an ex-student, Stephen Rowe. Stephen was a student here, and then he was a postdoc in Berkeley, and now he's back in Canada. I think he's retraining for to become a school teacher. So there's some very lucky students out there. But focusing on the topic, what we've been trying to do is to come up with an analytical theory to cover a portion of what we believe happens inside of massive stars to cause certain types of stellar outbursts. So what I want to do is to, I guess this talk is in 3 stages. First of all, why are we doing this? The second question is how. This is the more interesting question from a physics standpoint. And then the third is, so what? In other words, what are the important outcomes of having figured out why we should be doing this and how we should do it? Okay, so why this problem in particular? Over the past decade or more, actually, there's been an increasing number of types of outbursts and weak explosions associated with massive stars that have been observed in a variety of ways. These can include a number of events, some of which are probably of the type I want to talk about. So events having to do with massive star outbursts. So we might have LBV eruptions, supernova imposters, pre-supernova outbursts, and mass eruptions. And all of these are basically under the category of some massive star emits material in a way that you weren't necessarily expecting, in a manner that is not the same as its terminal explosion. So in some of these cases, what you may be seeing are eruptions that will precede a supernova explosion. And in particular, these mass eruptions are often determined after the fact when you have a supernova explosion and you observe something that indicates the presence of significant amounts of matter outside of the star. So those can include type N supernovae, which are supernovae that have a massive circumstellar environment, which lead to narrow line emission. There's also flash ionization of a dense circumstellar environment, which is sometimes observed in the early spectra of these supernovae. There can be, let's see, what's another example? Well, there can be events in the light curve phenomena. Such as early bumps in the light curve, or just things about the early light curve that don't fit your standard model for what the supernova ought to look like, and which you have to invoke some circumstellar material as the easiest way to explain. So these, and then there are others having to do with traces of the density of the surrounding medium that might have to do with the X-ray or radio light curves of your explosion. And I should mention that there are people in the astronomy department who work on this. So students of Maria Drought and Dasik Moon, such as Nilu Afsariarchi and Adeze Idrik. Okay, so we have a variety.
Chris,
Yeah.
can you hear if we ask questions?
I sure can.
Okay, good.
And please do.
Just to help me place the mass eruptions, perhaps as distinguished from LBVs, which also eject mass, is that a matter of how much mass is ejected?
What I'm going to focus on are situations where the kinetic luminosity of your star, or the overall luminosity, expands beyond its normal value and in fact above the Eddington value. So I want to focus on super-Eddington outbursts, which is a subclass of these things. And so there are definitely weaker eruptions which might be covered in this list that are not what I want to talk about because the theory doesn't apply to them as well.
Okay, and then out of curiosity, where would something like Eta Carina fit into this?
That's a mystery. That's actually a mystery. So there are hypotheses that the eruption of Eta Carina has something to do with its companion and maybe a previous companion that's collided with it. But there are also possible reasons that Eta Carina would have gone through its great eruption as a result of some of the same phenomena that I want to talk about. In particular, it may have been an example of the pulsational pair instability, which is an overall collapse and vigorous re-expansion of the core of a sufficiently massive star, or the sufficiently massive core of a star that goes through a phase of unstable, I think it's oxygen burning, and launches an outburst that way. So,
great. Thank you.
Yeah. So that brings up the issue that there are a few different reasons why stars might come up with these types of eruptions. And many of the ones I want to focus on, or all the ones I want to focus on, have to do with activity from the core of the star. So, so the theoretical motivation would include things like the pulsational pair instability, which I've just described, but it involves the softening of the core equation of state due to the creation of electron-positron pairs, followed by a collapse, but the collapse is turned around by energy injection from oxygen burning and increases the core entropy sufficiently that it has to recondense before it can go through that cycle again. But that whole process launches a wave out through the star. And there's some excellent papers on this topic, for instance, by Woosley and others. And what you see is that there's a wide variety of eruptions that can occur as a result of this, with the core itself going through sudden pulsations. There are also other events, such as there's vigorous, especially oxygen shell burning, which can lead to very high acoustic luminosities, and I'll get back to the question of acoustics in a moment. And then these are high mass stars, so we're sort of going down in mass in this list. And then at the lowest masses, there are shell flashes in what are called electron capture supernovae, which is at the low end of the core collapse spectrum. So these at the high end, you're quite likely going to be producing a black hole, and these events have to do with the upper limit for stellar mass black holes, which was violated recently by, or the presumed upper limit for stellar mass black holes, which was violated recently by gravity wave event 190521. So that's an intriguing tie-in to what I want to talk about. So this is the motivation Now let's talk about how. How do these events come about? But the how means two things for me. First of all, how do the events come about? And secondly, how do I want to approach them? So from a physical mechanism standpoint, I want to focus on phenomena that have to do with rapid energy outpouring from the core of a massive star, doing something at the surface that launches these outbursts. And sometimes what you see could be classified as a wind, but I didn't mention that in many cases you see very rapid velocities, which are almost certainly above the escape velocity of the star, and therefore are strongly indicative of shock ejection. So in particular, Nathan Smith has found many examples in Eta Carina and in other supernova imposters like 2009 IP, where the ejected speeds are up in the range which is hard to explain without having effectively a weak explosion that drives material off the surface. So the question is, what can the core do to communicate with the surface and cause this type of behavior? Well, there are a variety of ways that stellar cores communicate with their surfaces. The usual way is they just produce energy, and the energy comes out in normal radiation diffusion and convective motions. Radiation diffusion is way too slow to drive these outbursts. Convective motions are faster, but to drive outbursts above the Eddington luminosity on the timescales that we're talking about, the convective motions would have to be so fast that they would devolve into what I really want to talk about, which is sound waves. Sound waves that travel from the core of the star to the surface. And both because it's easiest and also because the sound waves that communicate best with the core are those of low angular momentum quantum number, low L. It's simple and probably not bad to idealize this problem in spherical symmetry so that you're down to something that you can really handle both analytically and numerically in on a piece of paper without too much work. That still doesn't solve the question of how you're going to do it. So, what I want to focus on then is the question of, if I have a piston, I'll just consider the core of the star to be a piston. Something is happening in the core of the star, providing a push, launching waves that are traveling outwards, and I want to understand what happens to drive material off the surface or drive these outbursts. How should I study that problem? Now, there are a variety of ways you could imagine doing it, and it's important to say, first of all, that this type of phenomenon is already covered within stellar evolution codes. So modern stellar evolution codes do not just, well, at least some of them, do not just evolve the system quasi-statically through a series of hydrostatic states, but when there's a significant change on the dynamical time, they'll cut down the time step and allow you to do dynamical motions. So that if there are wave motions inside the star, you could conceivably capture those. So in particular, some of the stellar evolution codes that would be used for this problem would naturally, if this core did something significant, they would observe within the code a wave which launches outward and then does something, dissipates, and perhaps drives material off the surface. However, I want to do this analytically, and the reason, partly because I just like doing things analytically, even if you can do them numerically, but also because it's actually a hard problem numerically in ways that aren't necessarily immediately obvious when you run one of these codes. And in other words, they'll give you an answer, but it might be wrong, and so you need to be careful about this. And the reason it might be wrong is that what I'm going to talk about are sound waves that travel outward from regions of high sound speed to low sound speed. And in the process, they're going to be amplified. And they're going to develop shock fronts, which are discontinuities in the flow that you have to resolve well in order to understand what this problem is doing. Now, the issue is that the dynamical time in the core is very short compared with the dynamical time of the star. And therefore, the wavelength of the sound wave is a small fraction of the stellar radius to start with. And it gets smaller as the wave moves out. And furthermore, if you want to evolve what we have learned, if you want to evolve these waves well with a numerical code, at least the type that we're using, there may be tricks to get around this problem, but you have to resolve the wavelength in about 1,000 zones. And that's a function of how many wavelengths this wave is going to travel before it does something interesting. So in the regime that you want to study, you actually would have to resolve the stellar envelope with many thousands of zones, maybe 100,000 zones across the stellar envelope, and use a high order hydrodynamical code to do this right, which is not a good description of the stellar evolution codes, which would have given you the core event that drove the waves. So that's just a note of caution, and it's a reason to want to do this analytically. So just as a preview of what I want to talk about, what I'm describing is sound waves. So this might be a depiction, for instance, of the pressure or the velocity as a function of radius. These sound waves will evolve in the way I've described, where as the sound speed goes down, the wave amplitude and the density goes down. The wave amplitude may have to increase in order for the waves to take the wave energy out from the core to the surface. But in the process, they're also going to develop shock fronts. And this raises the question of what is the right approach analytically to describe this phenomenon? So, well, actually, let me just back up for a second and say, whenever you have a wave traveling outward, I've talked about the outward transport of these waves and their dissipation in terms of the development of shocks. But there are actually three fates. So three possible fates that your wave could have. One possibility is that it travels out and damps. Another possibility is that it travels out and reflects. And the third possibility is that it travels out and forms a shock. So you have to be careful and make sure you understand which of these three is going to happen in any particular wave motion. And in particular, I'll give you quickly give you the argument that shocks are the relevant phenomenon for this particular type of wave. The reason is that, well, first of all, you can consider the question: is your wave going to reflect off of the changing situation that it's encountering within this massive star before any of these other things happen? And the particular reason that reflection is not a strong candidate for the behavior of these waves is this point that the dynamical times in the core are very short. And what that means is that the wavelengths are short and they get shorter as the wave goes out. And the criterion for reflection is that the conditions that the wave is interacting with change significantly over a single wavelength. That's long story short, that's the condition for a wave to meet an outer turning criterion and to reflect backwards. So if you consider a wave of a certain frequency, that will happen somewhere near the surface of the star, but the fact that the frequencies we're dealing with are relatively high mean that there's plenty of opportunity for one of these other two phenomena to happen before that does happen. Another possibility is that the wave will damp, and the dissipative mechanism here is the fact that you've got stellar fluid and there are photons that represent the thermal state of the stellar interior. And those photons diffuse through the stellar matter, and this happens naturally all the time because the star has a diffusive luminosity. And so there'll be a diffusion out of the peaks of the wave and into the troughs of the wave, and that's a dissipative effect. But it turns out, so let me just say, reflection doesn't happen because the frequency is much bigger than the characteristic stellar frequency. Damping is also a possibility, but damping turns out to be slower than the formation of a shock front, insofar as the wave luminosity is bigger than the radiative luminosity of the star. Because I gave a Blackboard talk that included this a couple of years ago, but the diffusion out of the wave is the same physical phenomenon as the diffusion that gives rise to the radiative luminosity. And there's a simple criterion you can write down, which is effectively, if your wave luminosity exceeds the radiative luminosity, then you'll shock before you hit a damping criterion. Now the shocking criterion is what that leaves you with. So what you have is a wave that travels out, it doesn't reflect, it doesn't damp, it forms a shock front. So you sort of have a single shock behavior. So this really
quick question.
Yeah.
So for the damping criterion, is this damping of the wave by radiative diffusion?
Yes, that's exactly right.
Okay, just making sure.
Yeah, exactly the same thing that gives rise to the radiative luminosity. It's just on a different, if you're damping the perturbation, not the overall gradient in the radiative energy density.
Okay, makes sense.
Okay, so so that focuses your attention on acoustic propagation of a particular sort. So that also informs the approach that you ought to take, because so that's the other aspect of this question, how should you approach this problem? So when you're faced with a problem in stellar oscillations, what the natural thing to do, which has been very successful in other situations, is to decompose the oscillations of the star into eigenmodes, into characteristic modes of the dynamics, and then there be some discrete spectrum of these things. That's Aaron. That's something I can compute. Is the fact that this spectrum will be discrete, and then you look at because the creation of shocks is a nonlinear phenomenon. Then you would have to look at the coupling between these linear modes, given their finite amplitude, and that is a way to study this problem, but it's not the best way to study this problem, specifically because what we have is waves that are traveling out in effectively a single shot motion, and so they never get a chance to reflect, which means that the dynamics that really imposes a set of eigenmodes on this problem never have a chance to work. So although it is possible to describe these waves in terms of the eigenmodes, it's not necessarily a good idea, because in effect you have an arbitrary motion of the piston of the core that drives wave outward. The wave shocks, and you form shocks which are discrete localized phenomena, which therefore are not easy to describe in terms of a bunch of couplings between eigenmodes. But they are easy to describe with a local phenomenon, so I want to focus on a local approach to discussing how this happens. Any questions about that? So we're sort of at the how portion of the talk. so I should mention there's another natural thing to do in this case is to apply the WKB technique. The WKB technique would be to discuss the waves in terms of a wave packet of high frequency with a slowly varying background, and then look at the adiabatic evolution of this wave packet. And then what I want to describe to you is effectively, it's very related to the WKB technique, but it's a bit of an extension. So the WKB technique is great, but the WKB technique also picks out a specific, the usual analysis picks out a specific frequency. And here we have a wave which is distorting, which is the creation of harmonics of the original frequency in the distortion of the wave. And I want to describe that now. So the place to start for this problem is really the very beginning of nonlinear hydrodynamics. So the very beginning of nonlinear hydrodynamics is the problem solved exactly by Riemann in 1890. So suppose we have a tube of material with perfectly uniform fluid, which is undergoing perfectly adiabatic acoustical motion, and we want to just describe the dynamics of this fluid. Riemann gave us a beautiful solution to that problem. I'm trying to figure out if I should give you the complicated or the simple version of the Riemann solution. I'll give you the simple one, I guess. Okay, so here's the equations portion of the talk. Let's talk about the motion of this fluid in terms of its mass and momentum conservation laws. And what I'll do is I'll derive what are known as the Riemann invariants for you very quickly, because they're related to the solution I want to show you. You may have already seen these, but not everybody will. Okay, so what I'm going to do is I'm going to write down conservation of mass, so the time derivative of density moving along with the fluid. So that's the partial time derivative plus the flow speed times the spatial derivative operating on the density is equal to negative density times the divergence of the velocity field. Okay, so let me just take that outside the tube here, and I'm going to write that in subscript notation, rho sub t plus u rho sub x plus rho u sub x is equal to 0. Okay, so now my x is my coordinate along the tube at the moment. A t subscript means a partial derivative with respect to time, and an x subscript means a partial derivative with respect to x. Okay, now I'm going to use the fact that the partial derivatives of pressure, so I'm trying to draw a p and not a rho, is equal to something called c squared times the partial derivatives of density. And c is the, c squared is just dp d rho, which is the same in this particular problem, regardless of how I've perturbed the density. So c turns out to be the sound speed in this problem. Okay, so I'm going to multiply through by c squared to turn this into the partial time derivative of pressure plus u p sub x plus rho c squared u sub x is equal to 0. So that's a revised version of the mass conservation law using this adiabatic rule. And then the momentum equation will be rho u dot, which means rho partial time derivative plus u times the partial space derivative. And I should mention this combination is called the convective derivative. This is time derivative moving along with the fluids and moving at speed.
Chris,
Yeah.
Another quick question. So does the adiabatic index show up anywhere in the second equation? Because I mean, so I thought like for the first equation you have on the top line, there's also a factor of the adiabatic index, which is like multiplied or divided by the sound speed squared. I could be misremembering that equation.
Yeah, I think you are, John. So we can take a look at this. We can take a look at this afterwards if you want.
Okay, yeah, not a big deal.
So that's going to be equal to negative divergence of pressure, which is the pressure gradient that drives acceleration. And so this is going to lead to the partial time derivative of u plus u times the partial space derivative of u, dividing through by rho, plus 1 over p, 1 over rho times p sub x is equal to 0. So these two equations are the ones that I'm going to use to get the Riemann invariance. And so what I'm going to do is I'm going to divide the first equation by rho c, by rho c, and add it to the second equation. So this is equation 1, this is equation 2. And okay, maybe I'll skip a step just to get to the final result. So we're going to wind up with the partial time derivative of u plus or minus 1 over rho c. Oh, and I should mention, I'm going to divide it by plus or minus rho c and add it to 2. So that I can come up with two possibilities depending on whether I chose the plus or the minus branch of this. Time derivative of p plus u plus or minus c partial space derivative of u plus or minus 1 over rho c partial space derivative of p is equal to 0. Okay, so what you see here is two terms, one of which involves time derivatives. There's a time derivative of u and a time derivative of p. One of which involves space derivatives, and the one that involves space derivatives has a speed multiplied onto it. So if I can say that this is the partial time derivative of some quantity j plus minus, and this is the partial space derivative of the quantity j plus minus, then I have the equation for j plus minus to be to have 0 change along a trajectory that travels at u plus or minus c. So that's actually, if you look at these terms, that's actually possible if we define j plus or minus is equal to u plus or minus the integral of dp over rho c. So in particular, if you have ideal gas law with a particular exponent p proportional to rho to the gamma, then this would become j plus minus is equal to u plus or minus 2c over gamma minus 1. So what this...
I just want to make a comment that so what you showed is the same derivation as it appears in Landau, Lifshitz, and Zeldovich and Reiser and other stuff. But in my opinion, there's also another interpretation for this for the Riemann invariant. So the idea, right? I think most people would have an intuition about sound waves, right? When you inside a sound wave, you have a relation between the velocity amplitude and the pressure amplitude. And the ratio is rho c, what you have at the denominator. So one way of thinking about it is, right, you have, instead of considering a wave that can have an arbitrary amplitude, you can dissect the waves into small wavelets. And in each one of them, the change in V would just be delta P over rho c. So if you want to know the change in the net change in V, you just integrate over this.
Yeah,
So
that's
it's an expression. I think it's just more intuitive when you think about it as a series of sound waves.
yeah, and in fact, that's what I want to use this for. But so yeah, your point is well taken. And in particular, it's possible to show that if one of these families of waves is not active, so one of them is constant, like J plus and J minus, and the other one has a perturbation, at least with small perturbations, the conservation of one of these families is related to an energy equipartition within the wave, so that the kinetic and thermal perturbations are in equipartition with one another. I don't know if that's related to what you're trying to say, Almog. Okay, so let me just quickly now show you what's next. So this is in fact an exact solution to the problem that Riemann posed in 1890. And this exact solution allows you to solve all sorts of things by the method of characteristics. So sometimes this is purely analytical, and sometimes it requires numerical simulation to do this method of characteristics. So if you have a space-time diagram, what we've done basically is to break the motion of this fluid, which is uniform fluid in a constant area environment, into right and left going sound fronts, and these things trace out particular trajectories. And the name for these things are capital C plus and capital C minus. So rightward going characteristic curves or trajectories, and leftward going characteristic curves. Or in the case of a star, outward and inward going trajectories. And along each of these J plus is equal to a constant. Along this trajectory, it might be a different constant along another trajectory. And same for the leftward going. I'll give it a double prime. Triple prime. So it's a function of which trajectory you're on. And the problems that you want to study become very simple when one of these wave families is universally constant, uniform everywhere. And then all the flow properties such as density and sound speed and velocity are then just a function of the other wave family. So if you have J minus as a constant and J is a uniform constant and J plus varies, then U, C, and rho are all functions of J plus, and that's known as a simple wave. So if you have an outward traveling sound wave with nothing coming back, that's an example of a simple wave, and that's what I want to talk about in the stellar context. Okay, so great, but the problem is, okay, there are a couple problems. First of all, so this is the problem that Riemann hit in 1890, which took some later work to get over. So what Riemann realized immediately about this problem was that if I launch a sound wave in my simple wave, suppose I launch a sound wave traveling to the right, so there's a perturbation in J plus, but J minus is equal to a constant, then there's this issue that the sound wave will travel to the right, will be described by the conservation along these characteristic curves. But the peaks of these waves travel faster than the troughs do, because the wave speed U plus C is a function of J plus. It's an increasing function of J plus. And so you have this shearing of the sound wave as it travels along. And eventually you have a situation where, I've actually sort of drawn it here, a situation where the wave becomes vertical at some place. And if you were to evolve that forward, it would actually turn over on itself. So what you have is an analogy, to make an analogy of something like waves arriving at a beach. When waves arrive at a beach, you have a situation where the peaks of the waves travel faster than the troughs, not for exactly the same reason, but similar. The peaks of the waves travel faster than the troughs, and if you're on a surfboard at this point, you'll want to start paddling really fast so that the time the wave curls over, you can catch the wave and ride it into shore. But sound waves are not transverse waves, they're longitudinal waves, and so we have instead a problem when we get to a double valued function here, because we can't have a tubular breaking wave at the shore. Okay, so this is a problem Riemann ran into, and the solution, of course, is that the waves will develop shock fronts. Now, then the question is, my perfect exact solution to this problem breaks down, and I need to have a way to solve what happens after we form the shock front. So the answer to this was actually suggested by Lev Landau and developed by Whittam. So the solution they came up with is to just cut this wave in a way that makes your function single valued, and to approximate the solution to the later problem after the shock forms in terms of a cut version of the sheared wave. Now, the two issues here, one is that shock fronts change the flow. And by cutting it, we're basically assuming that these portions of the flow are not affected by the shock front. Well, this one's okay, because that's actually upstream of the shock. And if you think about flow upstream of a shock, it's not going to be affected by the existence of something downstream of it, because shock is a phenomenon that travels at least slightly faster than the speed of sound. So the material up here doesn't even know that the shock exists. But the downstream material does know the shock exists, and there's a little bit of a change in the flow behavior downstream. But these changes turn out to be third order in the shock strength. So as long as the shock isn't very strong, the things that matter for the downstream flow, like a change in the entropy or the fact that the counter-propagating characteristic, the J minus, is supposed to be 0 in this problem, those two are not exactly correct, but they're correct to third order in the shock strength, which means that you can, to third order, just assume that the wave is unperturbed by the existence of the shock fronts. And then the solution is to make sure, if you want to know where the shock is, because you can put it at different places and still have a continuous function, if you want to know where the shock is, you have to conserve mass, energy, and momentum. And it turns out that in these diagrams for a linear wave, that's equivalent to saying that the area cut out on either side of this wave to make the shock transition is that those are equal areas. So this is called the equal area technique. And it's a beautiful extension of Riemann's perfect solution to the adiabatic flow problem, and it gives you the shock evolution at least as long as the shock is not strong. So it's not exact anymore, but it's a very good approximation. Okay, so that's one problem solved by Landau. The problem we have is that stars are not uniform tubes. Stars have a very dense core with a very high sound speed, and they have spherical area, cross-sectional area as you go out. So we have variations in the density, sound speed, pressure, area that this wave is traveling through. So we need a way to adapt the Riemann-Landau solution to the stellar context. So that's what I wanted to tell you about next. So let me just explain really quickly what, because I'm running out of time. Let me explain really quickly what the next step is. Okay, so well, basically, the next step is to re-examine what happens to these characteristics, such as J plus, if you encounter if you travel through a changing environment. So remember that the original formula that Riemann came up with was that the J plus quantity was not going to change along an outward traveling sound front. But if you put it through an environment which is changing, then you will get time derivatives. And it turns out, so I'm going to skip some math, it turns out that there's a way to represent those time varying changes in a compact form. So what I'm going to do is I'm going to define a new quantity, R plus, which is the square root of the cross-sectional area times the density times the unperturbed sound speed times J plus. And that's actually true for either of it. So I'm going to make it just a renormalized function, which is related to the Riemann invariance. And so this normalization factor would just be constant in the problem that Riemann looked at. It turns out that the changes of J plus along its characteristic can be expressed very compactly in terms of this R quantity, which is that the radial derivative of R plus minus along C plus minus is equal to R minus plus times the radial derivative of the logarithm of root. Just double check I get this right. Rho naught C naught over A. Okay, so this is a new equation that captures all these changes in the environment, changes in the density, sound speed, and area. So there's a renormalization, and then there's a new term here because Riemann had this right-hand side being 0. What this is describing is this is the process of reflection. So an outward going wave will encounter some changes in environment, and it will reflect. First, it will reflect because the inward traveling wave will encounter it and some changing environment. That will generate some non-zero value of the countervailing wave, and then that will change the amplitude of the outward traveling wave. So this equation captures the phenomenon of wave reflection, and it's actually not too hard to verify that you can recover the high and low frequency limits of wave reflection with this equation. But basically, all it says is that there's a modified Riemann invariant that you can apply for this changing environment. And when you have a high frequency wave, you can basically just ignore the entire right-hand side, and you're back to the problem that you have something like a Riemann invariant, which is effectively conserved or adiabatically conserved as long as the environment it's traveling through doesn't change too fast. Okay, so that realization allows you to just copy effectively the solution that Landau came up with. So we had in Landau's solution, we have some wave as a function of position, and the wave is going to travel out and become a shock. So this was originally, maybe this amplitude might have been J plus, and this x coordinate could be position. So now I'm just going to copy that over to R plus, and instead of x coordinate, I'm going to make a new rescaled y coordinate, which is not the spatial not the spatial coordinate anymore, but it's an interval you can write down having to do with the structure of your star. And then all of the features of the equal area method hold over from the simple problem that Riemann and Landau and Whittam solved to your stellar environment. Okay, so that's effectively a solution to this problem, but let me now tell you what actually happens as a result of that solution. I think I have time for it. Okay, so what happens as a result of this solution? Well, first of all, there are two types of shock fronts you can get in this problem, and it's not exactly obvious, but I've already drawn. So one type of shock front occurs when the wave is overtaking itself at a node within a continuous stream of waves. This location is special because there's a symmetry on either side of the place where the shock will form, and that means that in the equal area method, this wave will, in linear theory, be stuck at that location in the wave train. So that shock front will move outward at the sound speed, the unperturbed sound speed, because it formed in the node. So this shock was going to move outward at the sound speed. Even though it's a shock, and you say, well, shocks are supersonic, it's supersonic with respect to the upstream fluid, which is now traveling back to meet it a little bit in its reference frame. Okay, but then if I have some kind of pulsation, like I talked about the pulsational pair instability, if I have some kind of pulsation, then there's a first wave. And this first wave does not have symmetry around the place where the shock is going to form. I should mention, I drew the initial waveform, and I drew a diagonal line to represent the shock. That's because over time this wave shears, and so in the initial state, I can draw a diagonal line that will, in the later state, be a vertical line to represent the shock front. So I can actually identify all of the shock evolution in this problem in the initial waveform. I don't have to even look at the final waveform to know what's going to happen. Okay, now there's another type of shock which forms at an impulsive wave pulse. And this one is asymmetric around the place where the shock is going to form. So I might idealize that as a sudden start to a sine function, but doesn't have to be. It could be something which is sort of like that. It doesn't really matter. It just has to be not completely symmetrical. And in particular, you want a period of quiet beforehand. If you have a period of quiet, then your shock at some later time is going to look like this. This is the place where the shock is going to be. You have equal area above and below, but because of the shape here in this quiet region, that period above and below stretches out way off to the right. So we actually have two types of shocks. One which is stuck in place, and one which can expand away from the wave packet. So these are called internal shocks and head shocks. And if you could have a tail shock, which is like the head shock, but on the back. Okay, now these actually behave quite differently. In particular, so I'm not going to show you how this works out, but in particular, what you find is that you can write down as the shock evolves, what's the velocity of the post-shock state, I'll call it V2, divided by and I should use the letter U because that's what I used before. So the fluid velocity in the post-shock state divided by the fluid velocity that the peak of the wave would have. So this is 1 if the wave is right at the wave peak. But it's generally less than 1 because your wave is eating down into the wave profile. Your shock was eating down into the wave profile. So for the internal wave, this is proportional to 1 over your coordinate. As the wave evolves into its future. But in the external wave, or the head or tail shock, let's call this a shock, internal shock. Whereas in the external shock, head or tail shock, this is 1 over the square root of the coordinate. And this difference in behavior leads to a very
Chris, I think your audio went out. I'm not sure. Can everyone else hear it, Chris? Or
No, I can't.
okay.
No, I can't do that.
No, he bumped something, so.
Oh, okay.
the microphone is on the table, so maybe there is like a button. It's the.
Can you hear me now?
Yeah.
Okay, so yeah, there's a mute button apparently. I don't know what you heard, but basically I was trying to explain that these internal and head and tail shocks behave very differently. They decay very differently, and they decay very differently because the head shocks can expand away from the packet that is driving them, and therefore the wave energy doesn't catch up with them as fast, and it's really significant. Whereas the internal shocks are trapped, and the wave energy just runs into them from both sides, and that causes them to run through the wave energy much faster. So in particular, and this has let me show you the consequence of this. The consequence of this is that if I travel out through the star and I look at the wave luminosity, so let me talk about the internal waves for a moment. So before they form a shock front, they're traveling along at some constant luminosity. Then they form a shock front, and they have this decay of their wave luminosity coming from the fact that wave energy is running into the shock front. This decay of the wave energy is going to lead to deposition of heat and entropy within the stellar envelope. Now, what's interesting about this is suppose you started with a higher wave luminosity of exactly the same frequency. If you start with a higher wave luminosity of exactly the same frequency, you get this behavior, or a lower wave luminosity. These internal shocks, as they decay, they trace a particular pattern through the star that you can write down in advance. So in effect, once the wave luminosity hits the curve for a certain frequency, then it will decay, and it doesn't matter out here if you started with one wave luminosity or a higher wave luminosity. By the time you get here, you're going to be on this universal curve. So that's an intriguing phenomenon, and it's also the case that if you lower the frequency, so this is proportional to omega to the -2. So if you lower the frequency at this, take the same wave with the same luminosity, but lower its frequency and maybe expand its time scale, it will travel a lot farther before it hits its universal curve, because this universal curve is proportional to omega to the -2. So that's a really useful phenomenon. It means you can write down a formula for this behavior, which shows you where most of the wave energy is going to get spent, which is around, in the case of an internal wave, that's around the place where the shock forms. You just go out from where the shock forms a little bit. Most of the wave energy is spent there, and then there's this universal tail to larger radii. So this is a great formula for heating the stellar envelope, and maybe then driving a wind with a hot envelope you've heated with a super-Eddington wave. But it's not a formula for driving shocks off the surface of the star. How do you drive shocks off the surface of the star? You would then use these head shocks. So if you have the front end of the wave, that front end of the wave drives a head shock, which because of the geometry effectively of this equal area rule, that head shock is going to move on ahead, and it's going to eat through this wave energy much more slowly. So if you have a head shock, that head shock will have a significantly higher amplitude at any larger radius in the star. And in particular, as you approach the surface of the star, there's a couple things going on as you approach the surface of the star. Let's suppose that we have the density and sound speed decreasing towards the surface, and then we have a wave traveling out. So I'm going to draw the, so this would be the radius, here would be the stellar radius. Well, the stellar radius would be someplace where this goes to 0. And then we have a wave. Let me just try to describe what's going on. So it's one radius, it's got this amplitude. There's an increase in amplitude that comes from the conservation law of this quantity R plus, which is related to the wave luminosity. And I'll just mention the wave luminosity is equal to 1/4 R plus squared minus r minus squared in, at least in for linear perturbations. So that wave luminosity, the conservation of r is related to the conservation of energy and wave luminosity. So there's a particular enhancement of the wave amplitude that you would get from conservation of energy, but at some point a shock forms. This shock will then cause a decrease in the effective amplitude of the waves. It will have one decrease for the internal waves, and it will have another shallower decrease for the head shocks. Also the tail shocks, but the head and the tail shocks behave differently as the wave becomes nonlinear. So you get an N wave that travels in here, but then if you look at the very first shock in the N wave, it goes up to this other line. Now the thing is that as the environment as the sound speed goes down, the density goes down, the adiabatic solution goes up, and these head waves can actually increase in amplitude and become strong. So after they become strong, you can't use the theory that I presented anymore, but there is a self-similar theory for the breakout of strong waves. Okay, well, I've passed time, but let me just summarize by saying that this is all related to stellar outbursts, and in particular, it may have some relation to the upper limit of stellar mass black holes, because that is related to the question of how easily these pulsating cores, these pulsating massive star cores can eject envelope, and an envelope that might later on collapse to form part of the black hole. So if you have a massive hydrogen envelope, then you want to understand the evolution of these waves, where they deposit energy and how they eject matter. And it's at least possible that that isn't fully captured in the current stellar evolution calculations. Thanks.
Is there a question for Chris?
Yes, so I have a question. So, Chris, I'm trying to understand how because when I think about your solution, the situation that you're describing, I can think of two extreme cases, and I'm just trying to understand how, and I think what you're describing is some sort of an intermediate case, right? Because in the limit of a very small perturbation, then the wave would just propagate to the edge of the star without forming any shocks if the amplitude is small enough. If the amplitude is,
it would reach its reflection criterion, or if, depending on the frequency, it might damp first. So one of those two would happen.
Okay, so I'm neglecting dissipation for this minute. I'm just trying to think about what's going to happen in terms of just hydrodynamics. So right, in one case, you're going to be acoustic all the way to the end, and in the other, and in this case, the energy is going to be concentrated along the thickness of the wave train is going to remain the same. There's going to be no dispersion. And in the other extreme, you have something that basically behaves as a set of Taylor explosion. So the energy is going to be smeared on a distance that's comparable to its radius.
Eventually,
So,
yeah, but that's after you go through, I mean, what I've described as weak nonlinear effects
right.
that lead to the formation of the shock front, and even the evolution of the shock front here is a weak nonlinear effect. Right. And then only at the end, if you get the transition to a strong shock, do you then develop a set up, well, something more like a Sakurai explosion. But yeah, it's something that.
No, yeah, but even earlier, right? As I make the wave stronger and stronger, then as I make the amplitude higher, then the formation of a shock is going to be earlier.
Yes. Yes, as you for a given wave profile, as you enhance the amplitude of the shock, the wave will shock earlier. Yeah, exactly.
Right. So it seems to me like there's one extreme where the thickness remains the same, and when you what you see when you get to the edge or wherever it's dissipated, it's the same profile that was emitted from the center. And then there's another extreme where you just have a single shock that destroys all the information that used to be there, and you're left with just one wave. So
Yeah, well, actually, it's an interesting question. Yes, you destroy information, but you don't destroy all the information. So suppose you have, if you have a wave that does this, so it goes through 2 cycles, then you're going to get a head shock, which starts at the maximum point of the slope here. You're going to get an internal shock there, and there's no tail shock in this case because I would have to draw a wave that does this to get a tail shock. Anyway, so if I drew this, then there'd be a tail shock that starts there. So not all of most of the information is lost, but not everything. So one thing that's not lost is the number of shocks, because this shock will move ahead, that shock will be stuck at the sound speed, this shock will move back. And so you'll have 3 shocks all the way out, not 1 in this case. It is possible for shocks to overtake each other, but it wouldn't happen in this case.
I think the second shock is eventually going to overtake the first one, right? Because it's gonna ride on top of the wake.
No, it will never overtake the first one. I'll bet you money on it.
Okay.
Oh, why? I don't know. What do you like?
Well, first, what I would like is to know what's going to happen, but I can run a simulation. I can check it out. If
I can show you one.
Okay, but my intuition is right, because the second one is going to ride on top of the right. Your
code works really well for this problem. Rich is a good code for this, so we can do that.
Okay. Yeah, but even if we take your example, if you have more than 2 cycles, then then you can reduce everything to just 2 cycles. Maybe the first one is going to move fast enough, and because the speed of sound is decaying, then maybe it's going to accelerate fast enough. But if you have more than that, then you lose all the information behind the head.
No, it's really interesting to watch how this plays out. This shock moves ahead in linear, like quasi-linear, weakly nonlinear theory. This shock moves ahead just because of the equal area rule. This shock is basically stuck in place, especially if I drew it in a more symmetrical way. And this shock is going to move backwards according to the equal area rule. So before anything gets strong, these things are expanding apart away from each other. And then as they get strong, this head shock will accelerate away even faster. Basically because it has retained a bunch of wave energy that is now available to drive it, whereas this one has spent a bunch of wave energy, which ran into it more rapidly because it's stuck in place. And the tail shock actually, for nonlinear reasons, moves back even faster. So they spread away even faster as things become nonlinear. So that's why I'm quite confident I'm going to win our bet.
Yeah, but even then, in your case, right, the backshock is going to run into the center and be reflected, right? Because it has to converge to after enough time, it has to converge to a sort of Taylor solution.
So this shock is moving outward. It's moving inward relative to the rest of the wave, but it's just moving outward more slowly, basically.
I see.
So nothing. There is a reflection due to nonlinear effects once these waves become strong, but that's really second order here.
I see.
Good.
Mind if I ask a question? Or,
Yeah.
Okay, so at the end of your talk, you mentioned that.
John, you're loud. Can you just?
Okay. Can you hear me? Or yeah, the mic might be kind of fuzzy. Is everything audible and stuff? Or?
It's more than audible. I'm just wondering if I can turn down my volume a little bit. Okay. There we go. Okay, try again.
Okay. All right. So in the end of your talk, you mentioned that these acoustic waves, when they get closer to the surface, they steepen and they shock. But in your diagram, you didn't have the wave amplitude going to 0 very rapidly. My naive guess for how, if you have a wave that steepens into a shock, how it would dissipate is everything just immediately goes, all the energy is immediately dissipated and goes into the stellar interior.
Okay, so let me explain. Yes, energy is dissipated.
Yeah.
And let me try to draw that for you. Energy is dissipated. So let's suppose this is the initial profile of my wave as a function of maybe this is velocity as a function of position.
Mhm.
Now, if I want to know where the shock will be, I'm going to use my equal area method, which is assuming a weak shock. So we're dealing with a situation where the shock is not strong yet. I'm going to draw a diagonal line, and it's going to cut away equal areas of this diagram above and below. Okay, now I know exactly what time this corresponds to because of the slope of this line. Because there's a uniform shear, the velocity relative to the wave node of each characteristic is just a function of the height. And that's a uniform rate of shear in this diagram, okay? So if I draw a line, a diagonal line, I know that that diagonal line will be vertical at some specific time. So I know the relationship between time in the future, or in this, that's in the original problem. In my case, the time coordinate, the effective time coordinate is this thing that I call y, which I can calculate from the stellar profile. But this slope corresponds to a specific time in the future, and that means I know exactly how much wave energy will have interacted with the shock front. So effectively what's going on is that this wave energy is going to run into the shock front from so basically the shock front is going to run into this wave energy is the right way to say it. So the shock is going to eliminate this portion of the wave. So in a sense, as the shock evolves, this portion of the wave is going to be destroyed. That carries a certain amount of energy, and that energy is going to be deposited as heat inside the stellar envelope. So I know exactly when and how this wave energy is going to be deposited in the stellar envelope. I can write down a formula for the profile of dissipated wave energy if I know the initial waveform. So it's not the case that as soon as the shock forms, you lose all your wave energy. They have to interact, and they have to interact because the wave is moving at a different phase speed than the shock is. And they have to run into each other, and that takes time. And it takes a lot more time for the head shock than it does for the internal shock.
Okay, that makes more sense. Thank you. Yep.
Okay.
Okay, thanks again, Chris. I'm gonna.
Thanks, everyone.